Okay, so today's lesson is on resistivity. So as I've said to you before, and we've looked at the different ways of adding up resistances in series and parallel, resistivity is the basic building block, or one of the fundamentals that we do in electrical. We use it in electrical science, we use it in design. We work out to make sure that our cables, and we work out the resistivity of our cables to make sure they can handle the current. We do it when we do our testing. We make sure that the resistance of our CPC, we do all sorts of things, is to do with resistivity. So what we're just going to have a look at now is, so resistance. Now, a resistance of a cable is made up with lots of little resistances added together. So you've got an example here of a length of cable, L1, L2, L3, L4. Each part of that L1, L2, L3, L4 has a resistance, R1, R2, R3 and R4. So what we can see here, if you add all those resistances together, you get the total resistance of the cable. So what this little sign at the bottom means here means resistance is proportional to the length of the cable. So the resistance is proportional to the length of the cable. So the longer the cable, the more the resistance goes up. So if we have a shorter piece of cable, we get a certain resistance. If we double the length of that cable, we double the resistance. And we'll go through some more of these examples in a minute. So if this case here, in an example, if a cable has a resistance of 0.15 ohms per meter, what will the resistance of 320? Now, this is really important because we'll come to this in a minute. We've got ohms per meter and we've got meter. So we can literally just times these two together. So if we have this length per meter and we times it by this, we get 48 ohms. So we're just literally timesing the two together. In this example, we've got 50 meters of cable and it has a resistance of 0.01. What would the resistance of 500 meters of the same cable be? Since the resistance is proportional to the length, and we've got quite a nice little calculation here with new length, old length and resistance. But if we can look at this, so we've got here, we've got 500 meters and 50 meters. So we can see that the new length is 10 times. Yeah, if we just work that out into 10 times. So if we did that calculation, so the resistance would be 10 times that. So we times that by 10 and we get 0.1. So the new length is 10 times greater. So the resistance is 10 times greater. This is a slightly different example where we go smaller. So we've got 750 meters of conductor and it has a resistance of 0.013. What will the resistance of 150 meters of the same conductor be? Once again, it's proportional and we have a new length and an old length and resistance. And we look at this, and if we were to use a little bit of mathematics or basic arithmetic, we can see it's 1/5. Yeah, so we work out that actually we can do it in a calculation in our calculators using the buttons that we looked at before. But if we put this into our calculator, we would see it's 1/5. Yeah, so we're just working out it's 1/5 of that. So 1/5 of 0.013 is 0.0026. So that's just quite a nice example. So the next part of the cable and the next thing we look at is, and we will do some questions at the end of it and I'll go through everything with it, is the cross-sectional area. So we've looked at the length of the cable, how it goes up the longer the length. Now this is the cross-sectional area, the thickness of the cable. And what we're looking at is how the thickness of the cable, what happens there. Well, what we can see, and we've looked at resistors in parallel, if we have a thin bit of cable or we had a thicker bit of cable, the resistance of the cable reduces. So if we had a really thick bit of cable, so say we had a 1 mil cable, it would have a resistance And then if we had a 4mm cable, that resistance would have gone down because we would have added it in parallel. So resistance is inversely proportional to area. So the bigger the area, the resistance goes down. And I'll show you some examples here. So if a resistance of 100 meters of a certain conductor is 0.076, calculate the resistance of 100 meters of the same cable, but A, twice the cross-sectional area, B, 4 times the cross-sectional area, C, half the cross-sectional area, and D, 1/4 the cross-sectional area. So what we can see is straight away in A, because we know it's inversely proportional, if we've got the cable and we've made it twice as big, we half. It's simple as that. Twice we halve it and we get 0.038. So obviously with 4 times the cable, we would divide it by 4. So it goes down even greater. If the cross-sectional area for C, and we can just go back to C just to see what C was. So we're halving the cross-sectional area. So we're making it smaller. Yeah. So we divide it by half. We're literally doubling the resistance. And the same as if we have 1/4 of the size, we're dividing it by 1/4. So we're making the resistance go up. So it's inversely proportional. So if we have a bigger, fatter cable, our resistance goes down. And if we have a thinner cable, our resistance goes up. So this is example 5. And we're just going to go through here. So if a resistance of 100 meters of a certain conductor is 1.24, calculate the resistance of 500 meters of the same cable, but with twice the cross-sectional area. So first of all, we do our first calculation, which we did before. So we've times it by 5. Literally, we've gone 5 times the length, and we've worked out that we've got 6.2 ohms. So if we had 500 meters of one cable, we get 6.2 ohms. But what we're saying is we've made the cable twice as thick. And as we've gone twice as thick, we divide it by 2. So we're dividing it by 2. So we actually end up with a resistance of 3.1. So we end up with a resistance of 3.1. So now we get into resistivity. So we're going to look at resistivity. So what I'm just going to do is I'm just going to pause this for a second. And I'm just going to in here. So going back to the resistivity. So what we find is that every type of material that we use has got a resistivity. Now, for our calculations that we use, and you'll find in the regs book, there is a list of resistivities, and it's all recorded at 20 ohms. So what they've done is they've got a meter by a meter by a meter, and they've recorded, yeah, they've measured the resistivity. Yeah, it's a really low number. It's 1.7 to 10 to the minus 9. So if you imagine all those zeros there, this is where we need to make sure we use our calculators. So what we've got is we have fixed resistances. So someone has done this for us. So someone has worked out these resistances for us. So what we've got here is a calculation. What we've got is a little calculation. And what we've got is the resistance of the conductor in ohms. So we have a resistance of a conductor, a piece of cable. We have rho, which is the resistivity in ohms per meter, which is what we just looked at. Then we have the length, which will depend on what length of cable we're using. And we have A, which is the cross-sectional area of the cable, depending on what we're going to use. So it's quite a simple formula. It looks quite daunting, but all we're doing is putting some figures into that equation that we've got. Okay. Now, what we've got to be careful of is when we get cross-sectional areas, they are always quoted in millimeters squared. We have 1 mil squared, millimeter squared, or we have 2.5 or 4 mil. Now, in all the equations that we're doing, we use meters. So to convert millimeters squared into meters squared, we multiply it by 10 to the minus 6. So what you'll see in this next equation, you'll see 10 to the minus 6 appear next to the cross-sectional area. And all we're doing there is getting the millimeters squared into meters squared. So it's just a simple way of adding to the calculation. Now, so we have an example here. Calculate the resistance of 1,000 meters of 16 millimeters squared, single copper conductor, taking the rho, the resistance is 17.2 times 10 to the minus 6. Now that does look quite daunting. So what I'm just going to show you here is on your calculators. So what we would do, first of all, is we would type in 17.2. So we would type in 17.2. Then what we would hit is the bottom button in the very middle of the calculator that says times 10 to the minus 10 to times 10 exponent. So we hit that button. And what we then do is when we put minus 9. So now you can see in the equation, we have that first bit, 17.2 times 10 to the minus 9. Hit the times button, and we use our lovely button that we've got here, 1 over, where it goes over the top. So we have a top and a bottom. In the top, I'll put 1,000 meters. Then I'll go underneath. So I put 1,000 there, and then I'll type 16. And then once again, I'll use that button that I said to you at the bottom, that little button there, and I'll type in minus 6. So I've put all those details into the calculator, and I hit the equals button, and as you can see, hopefully from the result, we get that. So top. So we have a top and a bottom. In the top, I'll put 1,000 meters. Then I'll go underneath. So I put 1,000 there, and then I'll type 16. And then once again, I'll use that button that I said to you at the bottom, that little button there, and I'll type in minus 6. So I've put all those details into the calculator, and I hit the equals button, and as you can see, hopefully from the result, we get that. So it is simply putting all those details into the calculator. And this is where we have this 10 to the minus 6 over here. And that's because we're using 16 millimeters squared, and we're using meters squared everywhere else. So we just add that. So it's simply remembering to go through those 3 steps. So exactly the same here. We're using a different resistivity because it's aluminium, which is 26.5 times 10 to the minus 6. And we times by 100, which is the length of the cable, 25 millimeters cross-sectional area, 25 millimeters squared. Once again, times 10 to the minus 6. Put that into your calculator, and we simply get the figure of the resistance of that amount of cable. we simply get the figure of the resistance of that amount of cable. And once again, we're going to go through this again. So we've got 100 meters of cable, and this is 2.5 we're going to use. We always use the same, which is 17.2 times 10 to the minus 6 for copper. We type all those digits into our calculation, and we get 0.688. So if you were working out on a site, you can have a look in your on-site guides because they've got a lot of these calculations. But if you were using 100 meters and you wanted to check your resistance of your cable, and you had a reading and you wanted to check what it should be, this is how you could do it. And the last example is 100 meters of silver conductor, which has 15.9 resistivity. And we measure that, and it's 2.5, and we do exactly the same calculations. So we'll go through those in that manner. And we go through those examples. And what I'll do is I'll do a Jamboard, and I'll go through those examples with you on the Jamboard, and I'll show you how that works, and we can do that. So the last thing, and we did look at this a couple of times before, is volt drop. So as we've demonstrated in this lesson, the conductors themselves will have a resistance, and like any resistance will affect the current flow and volt drop in the circuit. The magnitude of volt drop will not depend on the resistance of the cable, but also the amount of current flowing through. So this is where we go back to a little bit of Ohm's law. Now in the regulations, you'll know, and we'll see when we come to that, that there is a permitted amount of volt drop depending if it's a power circuit or a light circuit. And we will go through in the design unit next year about volt drop. But this is just a simple example, a load with a resistance of 23 ohms. So we've worked out that it's got 23 ohms, is connected to a 230 volt supply with a cable that has a total resistance of 0.7. So now we've got to calculate the volt drop. So what we have to do first of all is we add the resistance of the load to the resistance of the cable. So 23 plus 0.7, and we end up with 23.7 ohms. Using Ohm's law, we work out 230 divided by 23.7, and that gives us 9.7 amps flowing. So we've got the amount of current that is going to go and flow through our circuit. So we've got the current that is flowing through our circuit. So we know that's flowing. We know this is in series, so we've looked at that. So now we work out the cable volt drop. So we work out our resistance of our cable. So we know we've got 9.7 amps flowing. We've just worked that out. So now we just want to see what is actually flowing through how much volt is going to go through our cable. So using Ohm's law, 9.7 and the resistance of the cable, and that gives us 6.79 volts. So we know that we've got 6.79 volts. So then the voltage across the load, so we work out we've got 9.7, and we charge the load voltage, which is 23. So we work out our voltage across the load is 223.5 0.1. So looking at Kirchhoff's law, we add the resistance together. So we add the resistance together. So we've got our voltage, which we worked out to be 6.7 for the volt drop. And we've got our voltage across the load, which is 223.1. And we add them together. So although it's not exactly 230 volts, the slight discrepancy can be explained because we've rounded the answers slightly. But we can see that Kirchhoff's law applies. Now, the interesting thing there is that the voltage that we're getting at the appliance is 223. Yeah, and you would always need to check that to make sure, depending on what type of circuit that you're doing, is you have enough voltage arriving at your equipment. Because when we look at volt drop, or we look at design, and also when we look at inspection and testing, it could be fault finding. It's one of the faults. So what I'm going to do is going to put this video back onto the classroom. I'm also going to put a link onto the classroom to all of the electrical science handouts, and I'll be putting a link above, and I'll also put in a link to subscribe to the channel on there as well.